Welcome to Academy. Today I am going to construct a unit circle afresh on this clean white board, and I am going to demonstrate to you the concept of errors and tolerances. What I mean to say is I want to construct a unit circle to the desired accuracy of 1 part per thousand. That means I cannot have an error more than 0.1%. That's my targeted accuracy. Let's see whether I am able to do it. We will also see how to use trigonometry to measure heights and distances, because I am going to physically measure the trigonometric ratios. And to do all this, I am going to use the following instruments: a compass, a set square, a protractor, and a scale. All these instruments you use in your geometry class, right? And it's really fun. So today we are going to have a little fun. First, I am going to use the set square to use its property of perfectly perpendicular corner to draw a perfectly perpendicular x and y axis. Okay, first I have drawn the horizontal x axis, and I am going to use the perfectly perpendicular corner to draw the y axis. I have drawn the x axis and y axis, and they are reasonably perpendicular to each other, as permitted by the level of accuracy of the set square. Next, I am going to measure out 1 foot on both x-axis and y-axis so that I can draw a reasonably accurate circle. I have marked 12 inches on the x-axis and 12 inches on the y-axis. I am not going to draw the full circle because I need all the space for calculation. So I am going to draw only 1/4 of the circle. Okay, let's go ahead on that basis. I'm going to use now a compass to draw the part of the circle. Here I have drawn the circle as accurately as possible. Next, I'm going to draw 2 tangents, one vertical tangent and a horizontal tangent. After that, I'm going to draw a radial line which is 60 degrees from the x-axis, and the radial line will be extended to meet both the horizontal tangent and the vertical tangent. Let's do it. I have drawn the tangents. Next, I am going to measure 60 degrees using this protractor and draw the radius line. Now we have our 2 tangents and the radius line. Next, I am going to draw a perpendicular from the point where the radius line intersects the circle, 2 perpendicular from that point, one to x-axis and another to y-axis. Our construction is now complete. Just for the sake of summarizing the whole thing, I will explain what exactly we have done. We have drawn x and y-axis with origin at O, and we have drawn a quarter circle, so to say, with exactly 1 foot in radius. And as per our earlier discussion, this circle is our unit circle. I have drawn 2 tangents, one vertical tangent and a horizontal tangent. And I have drawn a radius line which is 60 degrees from the horizontal, and I have extended the radius line to meet both the horizontal tangent and the vertical tangent. And as you have seen in my animation on trigonometry, let's imagine that there is a red object rotating around this circle and is now frozen at this point, which is exactly 60 degrees from the horizontal. I have marked the vertical component and the horizontal component of this red object by drawing a vertical line from the red object to the x-axis and a line from the object to the y-axis. So this is our entire system. Next, I am going to name each of the points for the sake of identification and easy calculation. I have marked this point as O. Let me mark this point as A, this as B, then this as C, then this as D, then this as E, then this as F, G, and H. I have marked various points here. Each point has a significance. For example, OA is the horizontal component of this red object. So OA is equal to cos of this theta. Okay, let me mark theta also. Theta equals pi by 3 or 60 degrees. So OA is cos theta as per the original definition, as per the fundamental definition of trigonometric ratios. OA is cos theta, AE or rather OH is sine theta. Of course, OB is radius, OE is also the radius R, which is 1 unit. OF is also radius R, 1 unit. BD is tan theta, BC is radius, BD is tan theta, then OD is secant theta, OG is cosecant theta, and FG is cot theta. I am going to create a nice table here. Next, I am going to measure each of these lengths to see whether they are equaling to the actual trigonometric ratio values and demonstrate the level of error in this diagram, and I am going to see whether I have achieved this level of accuracy or not. It is very unlikely because I don't think I have done a good job of it, but let's see. I have drawn a table here with 5 columns and each column represents something. The column 1 is line. I have named it as line. What does it mean? The line means line OA, line AE, line BD, and so on. Then each of the line represents the trigonometric ratio. Let us say OA means cos pi by 3, AE means sin pi by 3, and so on. Next is actual value. What does it mean? Cos pi by 3 is 1 by 2. Sin pi by 3, square root of 3 by 2, and so on. I want to convert these actual values in terms of inches because all these represent, the actual values represent the length of the line in foot, because this is a unit circle with a radius of 1 foot. I'm going to convert that into inches because my scale is marked in inches. And next I'm going to measure each and every line physically using the scale and list them out here. And after that, the lost line. I'm going to measure or calculate rather the percentage error of my drawing with respect to the actual values. How I'm going to do? I have the actual value here, then the measured value here. The difference between the actual and measured values divided by the actual value will give me the percentage of error. Let's do it. So we will start with line OA here. Then we will go to line OH. So we are starting with cos as usual. Why? At the cost of repeating, I am telling you, cos means x, sin means y. Since we traditionally write xy, we are going to follow the same order, cos, sin. Line OA is cos pi by 3. Then line OH is sin pi by 3. Then line BD is tan pi by 3. Then after tan, we get the reciprocal of cos. Reciprocal of cos is secant, and secant is OD, correct? Then comes cosecant. Cosecant is OG. Then finally cot pi by 3, FG. Let me extend these lines. Let's continue. So we have listed down the lines and the trigonometric ratio they represent. Then the actual value. Cos pi by 3 is 1 by 2. And if I am going to convert 1 by 2 in terms of inches, I have to multiply by 12. So if I multiply by 12, 1 by 2 multiplied by 12 is equal to 6 inches. So this will be 6 inches. Let me write down in blacking just to show the difference. Then sin pi by 3 is square root of 3 by 2. And I have to convert square root of 3 by 2 in terms of inches. While you can take square root of 3 as 1.732, multiply by 12, divide by 2, all that can be done manually, but at the interest of time, let's use a calculator. So it is 10.3923048456 and so on. Let me take it as 10.39. I'm not going to repeat inches here just to keep it little neat. Then tan pi by 3. Tan pi by 3 is Sine by cos, square root of 3 by 2 divided by 1 by 2, that is square root of 3. So this is square root of 3. Let me convert that into inches. It is square root of 3 multiplied by 12. So that gives me 20.7846. So we can take it as 20.785. Next is secant pi by 3 is reciprocal of cos. So 2 multiplied by 12, 24 inches. So next is cosecant pi by 3. It is the reciprocal of sine. That is, sine is square root of 3 by 2. So the reciprocal is 2 divided by square root of 3. And I have to convert this into inches. It is 13.8564. 13.856. Next is cot pi by 3. Cot pi by 3 is reciprocal of tan. Tan pi by 3 is square root of 3. Cot pi by 3 would be 1 divided by square root of 3. And converting that into inches, 6.928. So we have filled up the table with the trigonometric ratio and their values, and each of these values represent the actual length of the lines OA or AE and so on. But next comes the fun part. I want to actually measure these lines physically using the scale and see whether we are tallying with these numbers, and to see whether I am meeting this target of drawing a unit circle within this tolerance level of 1 over 1000. Let's see. Okay, first is OA line. So we have to measure in terms of inches. I'm getting a reading of 6/1/8 of an inch. Pretty bad. Then OH, let's see how I'm getting. I'm getting a reading of 10.5 exactly. This reading is also very bad. Next is the value of the line representing tan theta, that is BD. This is 20 and 5/8. Looks reasonably okay. Let us see. You must be wondering why I'm writing 1, 8, 5, 8, etc. That is because in my scale, each inch is divided into 8 subdivisions. So I'm able to measure 1/8 accuracy. Next is the secant theta. Let's see. So this is OD is secant theta. I'm getting 20 plus 3/7/8. So 23/7/8. Okay. Then next is OG cosecant pi by 3. That is OG. So I'm getting 13/7/8. The reading is 13 inches and 7/8 of an inch. So 13/7/8. Then finally, cot pi by 3. Let us see. So which is cot? FG is cot. So let me measure FG. I'm getting exactly 7 inches. So this is what I have got after physically measuring each of these lines. I don't think I'm meeting the required level of accuracy, but let me calculate. I'm going to convert this into decimals and calculate, and I'm not going to show you the calculations. I'll just calculate it and write it on the board, and we'll continue further. So this is the final result I have got. I set out to draw a very accurate circle, as accurate as possible with the kind of instruments I have with me, and I ended up like this. The error in each of these lengths, that is the length of OA, OH, BD, they all are quite significant. They are not negligible. For example, my cos pi by 3 line is off by 2%. Similarly, my sine pi by 3 is off by 1.06%. Then my tan pi by 3 line, that is BD line, is off from the actual value by 0.77%. My OD, that is the secant line, is off by 0.52%, and the cosecant line is off by 0.14%, and finally the cot pi by 3 line FG is off by 1.04%. So the percentage errors are quite significant, and the average error I got, I have just taken the arithmetic mean of these numbers, and I have got the average error in my diagram is 0.935%. I set up to achieve 0.1% error, whereas I could achieve only 0.935%. That's why whenever you set out to produce something, or whenever you set out to draw something, or whenever you set out to design something, you must identify the sources of error and determine the tolerance levels which you can accept. See, number one, the scale. The scales are marked in terms of 1/8 of an inch. So even if I go maybe one point here and there, the errors could add up. Then the pen itself, the pen tip itself is about 3 mm. So even if I move the pen here and there, that error could be pretty large because the pen itself is 3 mm. The next error is a parallax error. While I'm marking the points, I'm not just crouching down and putting my eye at the same level and marking it. When I'm marking it like this, there is a parallax error. It's a human error, which is actually avoidable if you take some more care. But that's an error. And all of this could add up. And the scale that I have used to draw the lines and measure the lengths. The scale is marked in terms of inches. The marking themselves may not be up to the desired level of accuracy, right? Possible. And finally, how do you improve the level of accuracy? I have got a level of accuracy of only 0.935%, whereas I set out to achieve 0.1% level of accuracy. How do you do it? Either you use a better instrument, use a better pen, so that finer pen, so that you can draw very thin lines. Be very diligent in your activity, be very diligent in your measurement, and finally, change the person who has actually done it. The whole exercise demonstrates that every error you do in your activity, they all add up, and finally, you end up like this. Thanks for watching. This table has actually demonstrated the concept of measuring heights and distances using trigonometry. What we have done, we have used the angle theta to measure the length, let's say BD or OA and so on. While measuring heights and distances, you define two kinds of angles. One, the angle of elevation, and another, the angle of depression. We will see more of angle of elevation and depression and the heights and distances, or rather measuring heights and distances using trigonometry in our worked out example section. But this gives you a basic idea. In the last two videos, we have seen what is a radian and we have calculated the trigonometric ratios for the radian value of pi by 3. In the upcoming video, I'll give you a method to fill up the entire trigonometry table for the radian values of 0, pi by 6, pi by 4. Of course, we already have pi by 3 and pi by 2. I would love to have you back again with Academy. Thank you.